Our next presenter is Tony Colaprete with Multi-Lunar Day. I think it should be Multi-Lunar Day, not Multi-Lunar, because that's more than... anyway, sorry.
Yeah, it is.
Polar missions with a solar-only rover. That's a tongue twister right there. Tony, and I'll 13 minutes.
I can't use the word RP, that's why. Thank you. These are the principal co-authors. Lots of people went into the ideas here. It's kind of a culmination of a lot of years' work studying this problem. So just jumping right into it, if I can. So a little bit of background here. A number of you have seen this and are familiar with it and have done similar analysis that there are areas on the moon that have quite a bit of persistent illumination, in particular, of course, at the poles. And we're interested in these regions from a polar, volatile, and in particular resource standpoint as well, because also in these areas where you have persistent sunlight, you also have persistent darkness. And looking at these areas and studying them, we realized, well, you know what? A lot of these are kind of close together, actually within traverse distance of each other. And this is a nice example of one that we've dubbed Nobile North, or North Nobile. Nobile crater is down here. Oh boy. Yeah, this is tricky. Down here, and so this is up on a ridge above it. This shows total integrated sunlight, or fractional sunlight, over about a 6-month period. Yellow and green areas are a lot of sun, meaning over that 6-month period, there's almost continuous sunlight. Areas are gray, those are permanent shallow craters. We are really interested in this place. Where is it? There it is, up. I know they can't see it on there. That is an area that also corresponds to a high hydrogen deposit, or a neutron depletion seen from orbit. And on the top graph, you can see, shows actually the integrated sun and total deep space network coverage for one particular area. We called it Nobile C. And you can see the orange bar across the top indicates it has nearly continuous sun for 6 months. And it is only a couple kilometers away from a lot of PSRs and a lot of areas with near-surface water ice stability. So we thought, oh, this is an interesting place. Well, I wonder what you could do there with a rover. And so we entered into a number of simulations of this, including with folks at Carnegie Mellon and elsewhere. So that's the wrong way. This is the right way. So we applied a number of tools that have been developed over the last few years for Resource Prospector onto this problem. Resource Prospector was meant to be a low-cost mission, so it was avoiding the whole plutonium problem of bringing a nuclear reactor or RHUs or anything else to the moon. And so it was designed to really only rely on sunlight and these kinds of areas of uniqueness which have both sun and shadow very near each other at the poles. So we generated over the years this tool that incorporates both our understanding of subsurface temperatures through thermal modeling. Matt Siegler and Dave Page have been instrumental in this, making very high resolution thermal maps for us, time-dependent maps of sun and line of sight for communications. Annie McGovern was at APL, did a lot of this work with us. And then also maps with integrated operation constraints from landing site areas, slopes, entry, lander line of sight, etc. And then finally, of course, digital elevation maps. We generated, using shape from shadows, new elevation maps with NAC stereo images with 1 meter posting. And we combine all of these things with models of the rover, from everything from mobility, battery capacity, comm, data management, etc. And have this tool now that we can really plan and really have some confidence that we can take advantage of these areas of both persistent light and shadow. So this presentation summarizes a couple of examples of those. There were a number of assumptions that we made before getting into this. We required measurements could be distributed across multiple lunar days. Of course, you'd probably want to put your highest priority measurements as soon as possible. We wanted to see what flexibility that we would get if we just said plan it whenever. So this, back to Jen's presentation, this is a great way to actually evaluate things like this in analog settings in terms of timelines and management. We used the measurement requirements developed for Resource Prospector on this, and I could talk to you about that. But it was a series of prospecting, drilling sites, and analytical gas chromatograph mass spectroanalysis. The effective speed made good. And by speed made good, that's a nautical term some of you might have heard of. It's the average speed over time. We limit it to these examples of 0.7 centimeters per second. Now the rover can drive 10 centimeters, 20 centimeters per second. But when you factor in decision time, comm relay, delays, et cetera, you're speeding along at a 0.7 of a centimeter per second on average. We think you can do better than that. Of course, in the estimated speed made good for Resource Prospector was 1.2. For Lunacods is about 1.5 was the max they saw. So it's in that family. That's typically what you'd expect driving on the moon. We modeled no sun survival by being very conservative. The solar rover designed here is not meant to survive the night, but we basically used all the engineering data we had for it, including thermal vac test data and everything else, to constrain, along with thermal models, how many watts it was needed for it to survive in darkness. It needs about 160 watts. This is not shutting down the rover. This is actually keeping up thermal switches, power conditioning, et cetera, because, again, it wasn't optimized to survive the night. So very conservative estimates. We basically, the duration of night survival was how long that battery could maintain those 160 watts to keep it above the minus 50 or minus 60 degrees centigrade survival limit. And there's lots more data I could share with you on that if you were interested. So where to try some of these traverses out was the next question. And what we did was we identified some regional candidates. Our best integrated data set was for a region in the North Pole region, a crater named Hermite A. And so it's maybe not the best, but it's representative of this kind of a mission. We were able to look at the net, you like tongue twisters, the net no sun. That's, yeah. That's an Elphic creation. So the net no sun is basically the integrated time in which you had sunlight there. So you want this number to be low. So red areas, you have very small numbers, meaning over about 3 months' time, we had very few days of no sun there. The gray, blue areas, bad places. That's actually, well, if you're volatile, it's a good place. But if you want to survive for a long period of time in sunlight or have solar power, that's a bad place. And we convolve those maps in with the areas we were interested in studying, and also areas that were traversable. So we then convolved this, anded it, if you will, with required sample environments. We had requirements on the range of ice stability depths we needed to visit, slopes, access, comm, sun, etc. So basically, we are able to study these then very completely in these regions to find, to look for traverses that met all of our requirements. This shows a different view of it. Again, this is Hermite A in the middle here. The areas circled are areas that have very few no sun days in them, and we studied a couple of these. I'm going to describe option A and option B. This shows, again, it's just eye candy. Shows the same thing, but from an oblique view. Area A and Area B with Hermite A down here in the lower right. So this is an example for option A, or Area A. On the left, we have a NAC mosaic. On the right is the net sun mosaic, or calculation for the same area. And what's overdrawn on these is a traverse example. The white circles, the smaller inner white circles, are 100 meters apart in radius, and then the outer circle is 1 kilometer. And the green lines indicate the path of the rover. This can be done by hand, but now the tools are fully automated with all the constraints, so you can actually go through here and find hundreds of possible solutions. This is one example. Each of the circles is a science station where we conduct prospecting activities, raster mapping, drilling, analytical analysis, et cetera, baking out the samples, and so on and so forth. And so you can see what's going on here. This is for 2.5 days. That's limited by the data set we were working with. It most likely could have gone beyond that. But what we do is, I don't know why I can't get this to work. What we do is we start at the center of the bullseye, the circular area is where we land, and then we traverse down in one direction to the lower part of the screen. That dark area is a permanently shadowed region. We drive into it, sample it, come out, process the sample, then we go back up to the same circular area, the bright area here on the right, so that we have time to survive the night, and then we go back up to the upper right and come back down. So basically it's a pedal-like strategy where you return back to the landing site area where you have a lot of sun. This shows it, that same traverse in a timeline fashion. What you have on the top is the rover timeline. It indicates where we've landed, the loss of comm, where we regain comm, and that's an important point. No matter where you land at the poles, unless you have no matter where you land, you'll lose Earth communications unless you have a relay satellite. The Earth sets, and that's what we assumed. Even if you're near sun. Thanks. We wait for sun to come back up and restart activities and continue on. The activities are all shown down there. They're all model durations, power, etc. The battery level is the black line shown below that. That's the modeled battery depth of discharge as a function of time. And the two gray areas around the 6th of October 2021, those are areas where there is temporary shadow. And you can see in this particular region, we're only having 24 about 24-hour periods of darkness. Very easy for us to survive. We don't even get, we barely get below 50% depth of discharge on the battery. Totally unoptimized system. So this is an area that you could just go on for at least 2.5 lunar days, no problem. Option B, we did the same thing, and this just kind of summarizes total duration of the missions. Again, limited ultimately by the data we were working with that we had produced for the integrated simulation tools. But you can see here, you can get quite a good distance driven, 6 kilometers, 3.3 kilometers, lots of drill sites. This 36 and 40 drill sites, you're really starting to actually get a very good characterization of regions this way. And the max separation, that's the farthest distance between any of those sample points, is quite reasonable too. And these are all very consistent with some of the geostatistical analysis that we've done to really put a hard number on what you need to do at the poles to characterize resources. So an example, we've now opened this up. We've seen many of these at the North Pole area where we've studied. We're sure they exist also in the South Pole area. We're now opening it up to alternate rover architectures. For example, what if you had a regional scout that did not rely on a direct-to-Earth communications, but actually talked through a lander, was a relay through a lander? This has an advantage of saving a lot of money and a lot of power, making things less more likely to have many potential rovers, for example. There's some specs are listed in the upper left there. Here, what we did was we looked at used the tool to look at the line of sight between the lander and the rover, and that's the orange area in this upper right here. And we plan to traverse here. Down the lower right shows ice stability maps and the various regions of ice stability, including a PSR this rover could visit. The bottom graph shows basically the depth to ice that it is sensing all the time. That long straight area is where we're sitting in sunlight waiting for comm to come back up. So if you had a comm satellite, you could keep going, keep going. The gray is actually the paleo ice stability depth that Matt Siegler predicted, and you can actually test a really cool hypothesis in terms of, do you see different volatile concentrations at depth where you would expect the paleo ice conditions to be the same as they are today. This one's pretty cool. This one went about 7.38 kilometers. There's others that we've had. Same kind of architecture, solar only goes 10 kilometers at these different at the slow rover speeds that we described. So you can really actually cover quite a bit of ground with this type of architecture. The last slide pretty much is you can take this one step further and look at rover nodes, swarms. And a number of missions in LEO are demonstrating this now, easily applicable to surface operations. Several groups have looked at this too. Here we have the limited range on the left of a single lander rover system, assuming a 4-meter lander antenna, 2-meter rover antenna, and a 3-kilometer range limit on the radios. The right shows if you add a second rover what your range expands to. Again, the outer bullseye circle is a 3-kilometer range from the landing site. So just adding 2 small rovers to this network, or an additional rover to this network, can greatly open up the traversable terrain. So in conclusions, it's really kind of interesting that you can find these multiple day traverse options with very conservative assumptions both in your traverse speed, the kind of terrain you can cover, and the thermal assumptions. And it's not a unique thing. There's lots of places at both poles where this will be applicable. You can cover a lot of ground, more than sufficient ground to meet the kinds of requirements I think we need to meet. And what's great about this, and Jack Schmidt mentioned this, that with these kind of exploration science returns, you get to do some replanning as a part of the mission. That downtime when the Earth is down and the rover's sitting there, you can replan for your second day as opposed to having to rush in and try to get it all done in the first day. And with that, I thank you.